Hello, everyone. This is Yichun from Cornell University. Today, I'm going to talk about smooth contextual bandit, which is joint work with my advisor Nathan and my friend Xiaojie. In this talk, we focus on the stochastic contextual bandit problem formalized as follows. For each time step t up to a finite horizon capital T, which is assumed to be none, the environment draws the context and potential rewards pairs RAD from a fixed but unknown distribution P. The agent, for example, a doctor in a healthcare application, observes the d-dimensional context xt like features of the patient. The agent then chooses an action, or often we call it an arm, based on xt and historical information. An arm corresponds to a drug given to the patient. Here, for simplicity, we assume there are two arms denoted as -1 and 1. Lastly, the agent receives the bounded reward yt corresponding to the chosen action, like the patient's health outcome. The overall goal is to minimize the expected cumulative regret RT up to capital T, which measures how inferior our algorithm is compared to an oracle that knows the true P, but not the realizations. An easy observation is that if we knew the conditional mean reward functions for both arms, here we denote them as FA, we know the oracle policy is to pull the arm with larger FA at each xt. However, we never know FA in practice, so modeling is needed. Let's see how people model FA in literature. Suppose I tell you that f is a linear function in X, but I only have observations up to 0.4. How does f look like on the rest of the support? Well, we know it goes straight to the very end of the support because it's linear. In Contextual Bandit, many papers assume f functions are linear functions of context X. Linear model allows strong model extrapolation and enables global learning. Consequently, little exploration is needed, and it has been shown that greedy algorithm can be rate optimal under mild assumptions. When the model is correctly specified, corresponding algorithms achieves low regret, usually of order polylog in capital T. However, linearity assumptions is often violated in reality, and corresponding algorithms can get linear regret when the model is wrong. In the other extreme, people turn to non-parametric function classes like Lipschitz functions. So suppose now I have this graph of FA of a Lipschitz f up to 0.4. What does it look like on the rest of the support? Well, we know very little about it because Lipschitz functions can be very zigzag. In Contextual Bandit, people also consider non-differentiable classes, essentially generalizations of Lipschitz smoothness. This assumption allows very little model extrapolation, so it necessarily needs to do frequent exploration. In fact, the optimal regret can be achieved by dividing the support into separate bins and run parallel multi-armed bandit algorithm in each bin. The learning process is very local. Moreover, the optimal regret for these problems is very high, usually much larger than square root t. In this talk, we consider the large range of smooth functions that lie between these two extremes. Our model is purely non-parametric, but enables modeling smoother differentiable functions. In particular, we aim to give a new understanding of the interplay between optimal regret, function smoothness, and global or local learning. So now let's talk about the assumptions that formally defines the smooth contextual bandit problem. The first and the most important definition I will introduce is holder smoothness. A function f is called beta L holder if it has continuous derivatives up to order floor beta, which is the largest integer strictly smaller than beta. Moreover, for fx prime, the approximation error of floor beta order Taylor expansion at another x is bounded by x minus x prime to the beta power. The high-level takeaway in this definition is that beta roughly indicates the highest order of bounded derivatives. Therefore, non-differentiable functions corresponds to beta less than or equal to 1, smooth functions corresponds to beta between 1 and infinity, and linear functions are a special case of beta equals to infinity. Since we care about the smooth function in this talks, we assume the conditional expected reward functions of both arms are beta L holder with beta larger than or equal to 1. And we want to characterize the optimal regret in terms of beta. Next, we introduce two technical assumptions that are commonly used in local learning problems. First of all, we assume that our context xt is distributed on a compact set X, and its density is bounded away from 0 and infinity. The second technical assumption is based on notion of C0R0 regularity. A set S is called C0R0 regular if for any point X in S and R less than or equal to R0, the volume of the intersection of S and the radius R ball at X takes up at least a constant portion of the volume of the ball. As an example, the square is regular and the star is not regular. In our bandit problem, if we denote the region where arm A is optimal as QA, we assume that both Q1 and Q-1 are regular sets. The graph on the right-hand side shows why this is necessary. If Q1 is not regular, we are forced to pull arm 1 frequently in Q-1 where it's suboptimal to learn F1 near the boundary, and this will necessarily leads to high regret. Lastly, we introduce the margin condition that measures how estimation error translates into regret. It says that the probability of the region where F1 and F-1 differs by less than epsilon is bounded by epsilon to the alpha. And we can see from these examples, as alpha gets larger, the difference between F1 and F-1 passes 0 more quickly, so it's easier to tell which arm is optimal near the decision boundary, and we should expect lower regret. Great, now let's talk about our algorithm. On a high level, our algorithm is epoch-based, and it gradually eliminates the suboptimal arm on different support areas. At the beginning of the first epoch, we divide the support into tiny cubes with edge length delta fixed as this. Since we have no information now, in epoch 1, we pull arm 1 and -1 with equal probability no matter which cube xt falls into. After epoch 1, we collect samples S on both arms, and we can use them to get local polynomial estimators F1 hat and F-1 hat at the cube centers, and extrapolate a constant estimator in each cube. This is mainly for the purpose of proving uniform convergence. Based on these estimators, we're almost sure that in some cubes, one arm is suboptimal, and we can eliminate the suboptimal arm. These cubes are shown in colors and will pull the seemingly optimal arm if xt falls into them afterwards. Also, there are somewhat cubes where our current estimators aren't sure which arm is better, so we pull each arm with equal probability in epoch 2 if xt falls into these white cubes. As we get more samples and more accurate estimators, we can gradually eliminate the suboptimal arm in more white cubes and push them into colored regions. So that's the high-level idea. There are only two remaining questions. So first, how to define the epoch structure? And second, how to estimate the decision regions at the beginning of each epoch. To answer the first question, our epoch structure is fixed as this. The key is that our epoch length grows exponentially. Theorem 1 tells us that if we use the samples from the kth epoch to fit local polynomial estimators with the optimal bandwidth, Our epoch schedule guarantees that the estimation error for the difference between f1 and f minus 1 shrinks exponentially for all x that's in a region where we get many samples on both arms. This highlighted condition arises in smooth contextual bandit problem because for smooth functions, the optimal bandwidth for local parametric estimators is much larger than the optimal cube size. We'll see how it affects our algorithm soon. Now for the second question. Suppose this is our decision region we used in epoch k. How do we update decision at the beginning of epoch k plus 1? Obviously, we only need to focus on the white cubes, and there are two types of them. Type 1 are white cubes where we can't get enough samples on both arms. Here we highlight them in green. Take this upper right green cube in the blue region as an example. Within the circled optimal learning neighborhood for local polynomial estimators, which is much larger than the cube, we can't get enough samples on R minus 1, so we can't get accurate enough estimator for f hat minus 1 in this cube. Fortunately, as it's guaranteed by our regularity assumption of the optimal decision region, being surrounded by regions where arm1 is optimal means that arm1 should also be optimal in this cube with high probability, so we can merge it into the blue region without incurring high regret. We can do the same thing with the lower left one in the orange areas, and after merging type 1 cubes, we get this updated decision regions, where we're left with only type 2 cubes, which are surrounded by other cubes where we randomize so we collect many samples on both arms. Theorem 1 guarantees that with high probability, on all type 2 cubes, the f hat estimators differs from the true value by at most 2 to the minus k. Therefore, if in a cube, one of the f hat is larger than the other by at least 2 to the minus k, we're almost sure about the optimal arm in this cube, so we push it into the colored region and pull the seemingly optimal arm in it later on. Otherwise, if f hat 1 and f hat minus 1 are close in a cube, we're still not sure which arm is optimal, so we keep it in the white randomization region. In this way, we get the updated decision regions, where we see the white randomization region indeed shrinks. And we make decisions according to which region the xt falls into in the k plus 1 epoch. And this subroutine repeats again and again until we reach the end of the horizon, and that's our algorithm. Finally, I'll talk briefly about our theoretical guarantees. We can show that when assumption 1 to 4 hold, our algorithm achieves regret at most this order. Moreover, there exists a class P of contextual bandit problems satisfying all assumptions such that for any algorithm, the in-class maximal expected regret is lower bounded by the same order. This shows that our algorithm achieves the min-max optimal regret. Let's look at this optimal regret. If we set beta equals to infinity as in linear bandit, when alpha is equals to 1, we get polylog regret, and when alpha is equals to 0, we get square root t regret. These are well known in linear contextual bandit literature. On the other hand, when beta is less than or equal to 1, this rate is the same as what people get in non-differentiable bandit literature. As a special example for Lipschitz bandit, the regret is t to the 1 plus d over 2 plus d, which can be arbitrarily close to linear regret when the dimension is high. I want to conclude this talk by showing this table. In short, our paper considers the smooth bandit problem that bridges two seemingly separated lines in literature, that's parametric bandit and non-differentiable bandit. Our paper fills in this important missing piece in the bandit literature and sheds light on the interplay between smoothness, learning complexity, and regret. So that's all my talk. Thank you and take care.